All right, welcome. I'm going to start out this series of videos here on discrete math, and this is intended to be a series of videos for computer scientists that are interested in learning the discrete math foundations that you might need to pursue, some of the more technical topics in computer science like analysis and algorithms. The purpose of this first series is to go through the idea of propositional logic. Propositional logic is a topic that can be explored in a lot of depth in the area of philosophy. But for the purposes of computer science, we kind of need to know a little bit more of the technical mathematical properties of logic, of a logical system, since logic plays a major part in both programming. If you're a programmer, you've probably already encountered it in your programming. And it's also an important part in circuit design, another major area in computer science. So let's get started with propositional logic and just take a look at what the basics are. So the basics of propositional logic are around a figure of speech called a proposition. This is just, again, sort of a technical term. Sometimes we call it an assertion if you're making it. So if you claim this, or if you're claiming a proposition to be true, you're stating it true in as a figure of speech, then we might call it an assertion. But the characteristic of a proposition that makes it a proposition, other than being a sentence or a figure of speech, is that it can have a truth value. It can either be true or false. And so the propositions, the sentences that I have listed here as examples are going to be all have a possibility of being true or false. So the first one here, snow is white. This is a characteristic proposition that you'll see a lot in philosophical contexts. It's sort of a quintessential sentence. It's true in virtue of sort of maybe what the definition of snow is. Of course, snow doesn't always have to be white. There's sort of subtleties here that you can dig into, that again, if you're interested in, look a little bit closer in the philosophical topic here. But on the surface, snow is either white or it is not. And we're going to assume in this case that this is a true proposition, one that expresses truth. The next one here is also a true proposition, 1 + 1 = 2. Now, the reason I've included this one, again, is as an idea of computer science as logic for computer scientists. You might encounter logic inside of an expression in, say, for instance, an if statement or a while loop or something like this. You might have this statement. You might say, if 1 + 1 = 2, then do something. Well, this would be true. And so mathematical statements are often propositions, but some mathematical statements are also not considered propositions. And maybe I'll talk a little bit about that as well. If we substitute in or out some variables, sometimes we might consider this as not being a proposition anymore until we know what the variable's value is. However, it's more common in computer science for us to have a statement not 1 + 1 = 2, but maybe if x = 2, where x is a variable. And we'll explore that in a little bit more detail in a future video. The final statement here is the President of the United States is Kanye West. I live in the United States. I'm not an American citizen myself. But I can tell you that this is not true. The President of the United States is not Kanye West. I'm recording this during the quarantine in 2020. So the current President of the United States is Donald Trump. Who knows? Kanye West may be a future President of the United States. I'm not willing to make any predictions on that matter at this point, but he's certainly not going to be the President of the United States, the next President of the United States, for instance. It will either be Donald Trump again in the election, or it will be, looks like Joe Biden is going to win the nomination, so we'll see. So now I crafted this sentence as one that I hope would be false if I continued to do this lecture in the future. So we'll see. Maybe Kanye West will become the president one day, but my expectation is this statement will remain false, well, at least for my lifetime. We'll see. So again, these are just examples of propositions. We might take a look at these in more detail as we go, but all we want to sort of address here is, do they have a truth value, meaning can they be said to be true or false? And each one of these we assign a truth value to. Other figures of speech exist that don't have truth values, and so here, propositional logic has nothing to really say about them. Some of them have something to do with propositions. Sometimes asking a question is asking about maybe the truth or falsity of a proposition. Whereas the bathroom, you want to know the true location of the bathroom, not the false one, for instance. Go away doesn't have a truth value. It's a command. It's an instruction. We might call this an imperative figure of speech. But this type of figure of speech doesn't have a truth value, but again, can sort of be associated with a truth value depending on whether you do it or not. Did you follow the command or not? We might say sort of ties into a truthiness or a falsiness for this particular statement. But again, these are not propositions, so they themselves do not have truth values. The last one here, wubba lubba dub dub, the catchphrase of Rick Sanchez, is of course just an expression, and it's just sort of an expression of maybe emotional expression. Supercalifragilisticexpialidocious, same sort of thing, is just meant to express some kind of emotion, and so itself doesn't necessarily have a truth value. So all of these are just other figures of speech, and like I mentioned, propositional logic doesn't have a lot to say about them, so let's just sweep them under the rug and focus on propositions. So when we start looking at propositions, there are a couple different kinds of propositions that we might want to sort of categorize as sort of a little a menagerie of different kinds of propositions you might encounter. The two that I want to sort of just pull out to start, they're not necessarily the most important, but they do have a privileged role. The first one here is a tautology. This is a proposition that's always true. No matter what, it's always true. Some of these propositions that we have up above here, for instance, the President of the United States is Kanye West. That one's currently false, but it could potentially be true, maybe in a future time, given some different circumstances. Snow is white is true. Again, we might be able to imagine circumstances when it is not, where there's the famous sort of rule of thumb, never eat yellow snow. There's sort of a good idea behind that. So maybe snow is sometimes not white. If it's not white, this statement could become false in certain circumstances, but in the general circumstance, or in the circumstance that the sort of assumed circumstance, this would be true. What about 1 plus 1 equals 2? And this is one you might want to ask yourself. Is this one that could be false? Could it be false? And if you, I mean, there's really two answers to this. If your answer to this is no, this can never be false, then I think what you're thinking to yourself is this expresses a truth about math. And 1 plus 1 is 2, and it will never be 3, and it will never be 0, and it will never be anything else but 2. And I think that for most of us, for the computer scientists in us, we should be like, yeah, okay, that's all I need to know to move forward. 1 plus 1 is 2. Let's put it away. But if you're thinking that, no, this one could possibly be false, there's the possibility of it being false. And let's maybe explore that in a little bit more detail, because I think this is an interesting idea. So, right, let's consider this. So I said 1 plus 1 equals 2. At least the way I've written it here, we've said this is probably true. Okay, but let's consider another example here. Here is an example. What about 1 plus 1 equals 10? Now, most of us, probably instinct, should say this is false. But some of us, again, if you've got your philosophy cap on, or maybe you've got your computer science cap on, you might say, wait a second, what do you mean 10? Do you mean 10, or do you mean 2 written in binary? If this is written in binary, this is true. So, which is it? Well, this is up to interpretation then. Okay. This is where we ask our communicator, whoever's talking to us, whoever said to us 1 plus 1 equals 10, we say, whoa, 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 whoa. Is that binary or is that base 10? Because if it's binary, it's true. If it's base 10, it's false. So we need to know that to carry that out. So even these questions might be up to interpretation, but once we have that sort of clarified for us, we should be able to determine the truth value afterwards. Now, there is the idea that in math, that if we don't have that ambiguity here in what each of these symbols means, if the symbol 1 means 1, if the symbol plus means plus, and so on, then if there's no ambiguity about that, then this statement is always true. It will never be false. And then it is an example of a tautology. And in some cases, as a young child, you may have just learned this 1 plus 1 equals 2 as a truth. And sort of the cool thing about young children is they'll often ask interesting questions. They might say, well, why is 1 plus 1 equal 2? Well, hopefully most of us have gotten past that philosophical concept and just accepted that 1 plus 1 is 2. And if you just accept it, we sometimes call this an axiom, a statement that we take to be true without any proof that it is true. Okay, we just accept it's true. And there are a number of axioms we take to be true in math, in logic, and in other aspects or other areas of our world. Okay, and maybe I'll talk about them as we encounter them. So a tautology is a proposition that's always true. I've argued that this statement up here, 1 plus 1 equals 2, is probably an example of a tautology, as long as we aren't mixing up what these symbols mean. But I've got another example of a tautology right here, which is I'm over 21, almost said and. I am over 21 or I am not over 21. Now, this is going to be a statement that is true about me. The statement, the word I refers to me in this statement, but it might refer to you if you were to utter it. But the interesting thing about this statement, if it were to be uttered by any speaker, no matter what, it would be true. Because no matter who says it, they will either be over 21 or they will be not over 21. And so think about that for yourself. One of those two branches is going to be true, and the way that or works, we'll see this in a second, means the whole thing will be true. And so this is also, it's an example of a tautology, but it's also an example of a proposition. These are all propositions up here, but this proposition is formed by using some simpler propositions and using what we call logical connectives, like or not. Okay, the simplest proposition here, I am over 21, we could isolate that and write it as what we might call an atomic proposition, like the ones up above here. It can't be split any further without making it not a proposition anymore. So that I am over 21, we've taken that, we applied a not to it, we joined it with an or, and using those kind of connections strangely gave us a tautology. This is sort of an interesting thing. And this is an interesting tautology. I had a friend back in college who, he wasn't very bright, but he did know a little bit about logic, and he realized that if he said that may or may not be true behind any question, that he would always be saying something true. So someone would express some interesting thing about math, and he'd say, you know what, that may or may not be true, and that way he would always be saying something true. Now that's not very clever, because of what he is uttering is a tautology, something that is always going to be true no matter who utters it. And so we usually focus on sentences that are not tautologies. Tautologies themselves, other than special interesting ones like maybe mathematical ones, tend to be mostly boring kind of statements like this. I am over 21 or I am not over 21. Now, tautologies might be a little bit boring, but are play an interesting or privileged role in math and logic. The opposite of a tautology, well, maybe not the opposite, depending on how you want to define what an opposite is, but certainly an opposite of a tautology is the contradiction. A contradiction is going to be a statement then that is always false or never true. And often we do want to isolate contradictions, because contradictions are statements that, because they can never be true, that sort of brings this sort of a side case. And remember, for some of these propositions up above here that we're not sure, they could be true or they could be false. Well, a contradiction is one that could never be true, so that means there's no possibility of it ever becoming true, given any kind of circumstances that we might envision. Okay, so for instance here, the one that I have an example of, this is one also formed from making or conjoining atomic sentences using connectives. Here, the ones I'm using are and not as well. I'm going to use I am over 21 and I am not over 21. That is something that just never can be true. Okay, and so often we want to find or isolate contradictions in our thinking, because if we find a contradiction in our thinking, it usually is a sign that we believe in something that is false. So if you find a contradiction, if you're thinking, you're logically thinking about your thoughts and how they play out, and you arrive at some contradiction, then that means something earlier on must have been false. And so in math and logic, this becomes very important, because what we're trying to do is we want to isolate truth. We want to find true statements, which means we want to find those contradictions and then sort of put warning signs on them saying, don't go down this path. There's only falsehood down here. And that way we can isolate the little islands of truth that is our knowledge. Now, I mentioned that this series of videos is more attuned to computer scientists. So when does this become important for us? Well, truthiness becomes important, as I mentioned already, in expressions like if statements or while statements. Those can get a little bit complicated, especially once you start using connectives like ors and nots and ands. But then also logic usually plays an important role when we're just trying to understand the flow of control in our program. We sometimes call this the logic of the program. And any time you've introduced a bug into your program, it's because, sort of like this, maybe you've got a contradiction. You've introduced something false, a false line, an incorrect line in there, and it upsets the process, the logical process that you want to carry out. And arrives at a false answer, and that's sort of the contradiction. You want a true answer. So in computer science, and I'll try and highlight this when we start looking at code examples as well, where our logic and our reasoning is going to come in. All right, so this has been a good sort of introduction to our notion of propositions. Propositions are the centerpiece of what we're going to talk about in propositional logic, and then we're going to use them. So we're not usually going to focus in on specific propositions like snow is white. Instead, we're going to give this one a name like P, and then we might say, well, what happens if I take P and I and it to Q and I or it to not R, and so on, by joining these sentences together. If the original sentences were true or false, what happens to the final complex sentence that I join them together? So that's going to be my next goal. The last point I'm pointing out here is when we do create a variable for our proposition, we usually use lowercase letters from the normal English alphabet. We usually use P, Q, R, S, P for proposition, and then just sort of iterating through if we need more. Occasionally, we'll jump to the front of the list ABCs. We'll try and avoid the end of the list, the XYZs, because those usually look like variables in in some kind of maybe calculus or in some kind of algebra. And then for the same reason, we try and avoid sort of N, M's, and L's. They play usually privileged and important roles in the analysis of algorithms that we'll see later on. So you try and pick your letters so they don't overlap with other ones. So P, Q, R, S is sort of the ones privileged by propositional logic. All right, here we can now sort of explore these connectives in a little bit more detail. The first idea that I want to go with here is the standard connectives that we know in using computer science are and, or, and not. So the first one here, snow is white and the President of the United States is not Kanye West. This sentence, I've taken two sentences from the previous examples and put them together to make a true sentence. So snow is white, again, we're going to take that to be true, although we can imagine circumstances it would be false. And then the President of the United States is Kanye West. We took that to be false, but by negating it, by adding the not in there, we get a statement that is now true. Putting them together with an and makes a true statement. And we'll explore this more detail in a second. The second example here, if it is sunny outside, then we will go for a picnic. This is a very common expression of, this is a proposition that you might hear, someone express, your family member express, if it's sunny outside, then we'll go for a picnic. And hopefully, if you're an adult English speaker or even a competent child English speaker, you understand what this means, okay? You know that if the proposition, the atomic proposition, it is sunny outside, depending on its truth value, true or false, you will get a prediction about the truth value of the going for a picnic part, okay? So we know that if this one is true, if it is sunny outside, true, then we should expect this part is true too. We're on a picnic. What happens if this part is false? Well, I'm going to leave that up to you to think about for a second, because there's sort of an ambiguity there, and I'll highlight that. So if it is false, if it is not sunny outside, are we going for a picnic or not, if this statement was true? The last one, this one is not true of me. I am both a pirate and a ninja, but this would be a completely different statement. This one says, I am neither a pirate nor a ninja. And I wanted to bring this one in because this word here, nor, I'm not trained in any other languages. I know a smattering of Spanish and Japanese, but not enough to know if either of those languages has a nor operator. Okay, so nor is a word that means not or in English, and we'll again express this or flesh this out a little bit more as we explore it in a second. But it's got an interesting logical state. But again, if you are an English speaker, native, if you're not, then you may not have encountered nor before yourself. But if you are a native English speaker, hopefully, if you read this sentence, I am neither a pirate nor a ninja, you know the answer to the questions, am I a pirate or am I a ninja? And I sort of hinted earlier, I said I am a pirate, I am a ninja, then this is not true then. Okay, hopefully all about, and one of the things that I'm sort of trying to express here, and maybe this is a good point to note, that propositional logic and logic in general is not something new to us. When you start learning, calculus, you've probably never encountered that before. It's fresh, new idea. But logic is something that's built into our brains. Okay, it's it's what we do naturally all day long. And it's so ingrained that it is what we normally would call implicit or intuitive. We don't necessarily notice that we're doing it when we're doing it. Okay, in the same way that we don't focus on walking when we're walking or talking when we're talking. But we did have to learn how to do those when we were younger. And when we were learning about them, we maybe had to focus on them. The same way we did with logic. We learned logic when we were younger. We learned how it worked. We maybe made a few errors along the way, but we did it implicitly or intuitively. So it's already built into our brain. And so what we're trying to do here when we're studying propositional logic is we're actually trying to explore what our brain is already doing naturally for us. And this was sort of the cool thing that Aristotle did. Aristotle is often claimed to be the founder of propositional logic because he was the one who went through the process of analyzing his own thought process, focusing in on what his own brain was doing from that reflective standpoint and saying, what do we really mean when we say and? What do we really mean when we say if then? And so on. And he characterized this, and he was able to take what we implicitly do, each one of us implicitly do, and make explicit. Take that, codify it, write it down in a series of rules and say, this is what we're doing. Okay, and that's what propositional logic is. That's what we're studying right now. It's sort of the outcome of that. He was the one who sort of started that process off over 2,000 years ago, and here we are today, still relying on that benefit. Again, so now we're going through that same series of steps that he did. We're taking what we do implicitly and we are applying it. We're trying to pull out the explicit formalization of it. So let's look at this a little bit more closely now. Let's explicitly try and say, what does not mean? What does and mean? What does or mean? And so on. So here I've got a list of a bunch of different connectives. There's more than this. These are the standard ones. In fact, as far as unary and binary connectives go, unary means you only have one argument. Not is the only one of interest. The other one is just the identity operator. Identity of P is P, so that one is not interesting. And then we have all the binary operators, and in fact, these are all the binary operators that are interesting. The other binary operators, sort of like the identity operator, are not interesting. And so this is sort of an exhaustive list of them. But these are all of the normal operators that we would normally use in English expression and in most natural language expression in most languages. You have ways to express this. So negation or not, to say no, to take a true sentence and make it false, or vice versa. Conjunction, take two sentences and put them together. The whole thing's true only if both of them are true. Or has an interesting, we only need one of them to be true. With there's some ambiguity here. I'll come back to that in a second. All three of these operators, if you're already a programmer, there are symbols. I've used Java symbols here, but that's because my students are usually Java programmers. But you might be a C programmer. We use the same stuff. Java inherited from C, or if you're in JavaScript or something else. Almost all of these languages borrow these same symbols, so these are fairly common programming symbols for these same operators. And if you already are a programmer, then you've already sort of explicitly formed an idea of how these work. Okay, and so you probably use them in your code already. Not necessarily as common, maybe if you use circuits or some other type of notation, you sometimes see, because and has a lot of, it corresponds to the multiplication operator in certain ways of looking at it, mathematical ways of looking at it, it corresponds to multiplication. So sometimes we use the dot or the times, the x. And then or is sometimes also corresponds with plussing, so addition, so we might use plus. And then you might see negation as a bar written as well. These are just other symbols you'll see. The symbols that I've got over here are the ones we use when we're specifically using propositions in propositional logic. And these are not circuits, or these are not expressions in or variables in some program. These are propositions in a logical system. So we use these symbols here. So and sort of up here, up pointing arrow, sort of a shift 6 on the keyboard, but I'll maybe mention, if you're a latex, if you want to learn how to use this in latex, this one is called /wedge, this one's a V, and so on. So there's different ways you can make them. This means and, this means or, and then we have these other interesting ones. I mentioned if then in our example above. I'll talk more about that above. We call this an implication sometimes, or a conditional. There's different names for it. And then another one, which when we want to emphasize in our language the biconditional nature of it, we call it an if and only if, but you'll usually only hear that from mathematicians or logicians. Okay, logician is someone who does logic. And so if only in those contexts would you really hear someone say if and only if, because there's an ambiguity in English language. We'll sometimes just say if then when we mean if and only if. And I'll point that out here in a second. Before I get to the ambiguities in some of these, the English usage or the natural language usage of these connectives, I'll invite us to look at truth tables for each of them first to see how they work with the truth of the propositions together. Now again here, in case I brushed over this a little quickly, as I mentioned on the previous slide, we're going to use variables like p, q, and r to represent a sentence, usually, or a proposition, usually a atomic sentence. So here, these are all conjoined with ands, nots, ifs, and so ons. But on our previous slide, when we just had snow is white, that's an atomic sentence, we might give it the name P, and then we could put not P, which is snow is not white. Okay, P and Q, we pick two atomic sentences, join them together, and we'll get a new sentence. Now we can always conjoin a conjoined sentence to another sentence, but at the bottom level, we start with atomic sentences, ones that cannot be broken any further. So here the P's and the Q's are just references to some propositions. All right, so next up, I mentioned I want to show truth tables for our different connectives. Now, the way you would normally define how an operator works, if you wanted to do it explicitly, would be to give a truth table for it. So let's start with our first one, which is kind of the easiest one. This is the truth table for not now, or negation. Now, in your table, what you're going to do whenever you want to make a truth table, you're going to take the propositions that are in the sentence that you want to find its truth values for. In this case, it's just P. P is the only proposition in not P. And you want to list all the possible assignments of truth values to it. So here, P could either be true or false. So that's sort of the left-hand side of the table. Then the right-hand side, the definition of not, is going to tell us what this sentence truth value would be, given what we know about P. So if P is true, not P is false. And if P is false, then not P is true. And so this is a definition of how negation works. It just flips the truth value of the proposition. Of course, again, plug this into your internal logic computer. We all probably already know this. No surprises here, right? And if you want to explore this a little bit, just pause the video and think, what is the logical truth table going to be for and or? Those are the next two I'm going to do. So pause if you want. If not, here we go. So the next one here is going to be and. Okay. Now, making the truth table when you have two variables is a little bit trickier. So let's look at this here. We need all combinations of their truth values. Now, normally, there's a couple ways to do this. One of them is going to iterate like we did here, true, false, all the way down. And then the next one's going to do that in blocks of two. So we have two true, two false. And what we'll see, that will give us all combinations. True, 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 false, false, true, and then false, false. And this is the order that I usually put them in. You might see them in, starting with false, false is sort of a common way as well. If you treat these as zeros and these as ones, this seems sort of backwards. But starting with truth is also common because, at least in logic, truth is usually considered to be the primary or default state, and false is sort of the negation state of it. But let's look at the truth table here. So for P and Q, we now have true and true equals true. This is going to be the only circumstance that the sentence P and Q is true. And again, think of this as in your own mind, plug it through your own logical computer. If one of the sentences is false, then it doesn't matter that the other sentence is true. The whole thing becomes false. Okay, so snow is white and grass is blue. Because grass is blue, the whole thing becomes false. Okay. Of course, if both of them are false, then the whole thing is false too. So again, think about your logical computer for and here. Does this make sense? Yeah, hopefully this lines up. What about or? What would change in the case for or? So in or, I have, again, all my combinations listed out here, same order as before. But now you only need one or the other to be true, right? If we change that, snow is white or grass is blue, that becomes true now, because it doesn't matter that grass is blue is false, as long as snow is white is true. Okay, so again, if either of the two happen to be true, P or Q, the whole thing becomes true. So that's our standard usage of or. There's an ambiguous usage of or, and I'll talk about that here in I'll mention it now. I'll give you the truth table for it. Sometimes we mean not when both are true, and I'll give an example of that coming up in a second. So this we'll call exclusive or, if we want to distinguish it from this or, which we'll call inclusive or, including the case where they both are true, excluding the case where they both are true. We'll also have now our conditional. Now this is the one place where our internal logical computer, the ambiguity in it can get mixed up. The ambiguity in or can sometimes mess us up, but usually the context of our discussion, if someone says or in the exclusive or way, you usually know that they mean it. Whereas in the if-then statement, sometimes the ambiguity is a little bit harder to cash out. So let's look here. What happens if P then Q? Now, let's go through a couple scenarios that are going to make sense first. If P then Q, okay, the one that I want us to think about here is the example we had on the previous slide. If we, what was it? If it is sunny, we will go for a picnic. Okay, something like that. If it is sunny, we will go for a picnic. All right. So if it is sunny outside and we go for a picnic, then that statement is true, right? So if it is sunny, then we will go for a picnic. If both of those are true, then we've satisfied the conditions, and we can say that if we take the statement as a promise, then it sounds like we satisfied the promise, right? If our mom said, "Don't worry, if it's sunny outside, we'll go for a picnic," then if it was sunny outside and we did go for a picnic, we'd be happy. Okay. Let's look at the next case then. Let's say it was sunny outside, but then we didn't get to go for a picnic. Now we're mad, right? Why? Because what our mom said, she said, if it was sunny outside, we'll go for a picnic. Okay, so we should be upset. She lied, right? It was a false statement. Okay, so that happens when if it was sunny outside, if P was true, but Q was false. Okay, now you'll notice if you see here, that's the only false in our list. So let's go through the other two cases and see if they make sense. Okay, I actually want to start with the bottom one because this one makes more sense. So if it's not sunny outside and we don't go for a picnic, then it sounds like that still said it sounds like our mom didn't lie, right? She told us if it's sunny outside, we'll go for a picnic. So if it's not sunny outside, no promises, right? Basically, that's what she said. But here's where the ambiguity comes in. It really is no promises. If it's not sunny outside, it's no promises. It's not necessarily we're not going for a picnic, okay? That's where this other case comes in here. If it's not sunny outside, well, mom might still be generous and take us for a picnic. Then did she lie above when she said if it's sunny outside, we'll go for a picnic? No, she didn't. Because actually that statement, if it's sunny outside, we'll go for a picnic, says something about it being sunny outside, but it doesn't say anything about the other case when it's not sunny outside. And this is something that can trick us up sometimes. This true here, a lot of students sometimes are going to say, no, that should be a false. Well, there is a truth table where it's false, and that's this one here called a biconditional. But there's an ambiguity between these two statements. And there's actually one other truth table where we swap this false and true, which is ambiguous as well. And because of this ambiguity in English language usage, we're going to want to be very careful when we start translating English language into logic, noting that we can't just sort of straightforwardly take an if-then and assume that it gives us this truth table. It might give us this one, or vice versa. We can't assume it'll give us this one when it might give us this one. Now this one's called a biconditional because the implication goes both ways. Okay, so if we took our mom's promise and we tried to state it this way, it would be, if it's sunny outside, then we will go for a picnic, and if it's not sunny, we won't. Now that's kind of a logic, we might call this logic ease. We start saying things in weird ways just to emphasize the logic of the statement. Okay, so another logic ease way of saying that would be, it's sunny outside if and only if we go for a picnic. Now that is very unnatural. No mom would ever say that, except maybe a high-level logician mom. I'd be scared of that mom, you know. You'd better have your logic homework done if she's giving you statements like that. Because we use natural language, and natural language is ambiguous. So let's actually explore that ambiguity a little bit here. Let's do it with or first, because I think this one's going to be a little bit easier for us to wade through. Let's look at our two examples. So you must be 12 years old or accompanied by an adult. This is like to get into the PG movie or the mature movies or whatever it is, right? You need to be at least 12 years old or accompanied by an adult, something like this, right? So what happens if you are 12 years old and you're accompanied by an adult? Do you get kicked out? Hopefully not, right? And this is our standard use of or. This is inclusive or. Most of the time when we mean or, this is what we mean. It means either P or Q. So either you're 12 or you're accompanied by an adult, or both. You could be both, and you're still let in. Okay. Again, we call this one inclusive or. And this was the truth table that we looked at here before, where if one or the other is true, but also if both are true. So if you're 12 or older, or you're accompanied by an adult, or both. Okay, and here's a common one. I was trying to think of a good common example in natural language. Say you're reading a menu and it says your meal comes with a soup or a salad. Now, usually the or in this statement means it comes with a soup or a salad, but not both. If you want both, usually it's an upcharge or something like this. Okay, so the idea here is that we call this exclusive or, right? And the idea is that we exclude the possibility of both. And sometimes, and there's a lot of cases in natural language where we actually mean this. You know, you or your brother can come in the car. That usually means one or the other, not both, right? So there are a lot of times when we use or that we actually are expressing exclusive or, and then there are other cases where we express inclusive or. Okay, now if you're looking at this video because you're studying philosophy, then you might be translating sentences into, logical statement. You need to be sensitive of when you look at a sentence and you see ors, do you mean inclusive or exclusive or? And then if you're a computer scientist, when you're crafting a statement, a logical statement, maybe in a if or only, or in an if statement, sorry, and you want to say, if x is greater than 1 or y is greater than 1, and you mean exclusive or, then you can't just put the or operator in, because it uses inclusive or. It uses this truth table. If they're both greater than 1, it will still be true. You need to come up with a better logical expression that handles exclusive or. I'll leave that for a later video to talk more about that, okay? And we will tackle that. So here's the ambiguity in English about or. What about if? Okay, so this is the one I was saying is sometimes a little bit trickier. Let's look at 3 examples here. So the first one here, I've got an example. If you get a 4.0, then you will graduate. I'm trying to make this one a little bit more clear than the if it is sunny, we will go for a picnic, because the if it is sunny, we will go for a picnic is one that tricks people up more often than not. It sounds to people, especially if it was given to you by your mom, it sounds like if it's not sunny, we're not going for a picnic, even though that's not necessarily implied by the expression. Here, if you get a 4.0, then you will graduate. This sounds like a reassuring statement. You might tell a student, don't worry, if you get 4.0, you're going to graduate. But it does not imply, so think about it yourself, put it in your own logical computer. If you graduated, did that mean you get a 4.0? No, not necessarily. So this normal implication, this is what we'll call the standard implication. This is the one we looked at before with the truth table right here. It means if P is true, then Q is true, right? But if not P is true, then there's no promises, either Q or not Q, we don't know. Okay, so that captures these two here, right? So if P is true, then Q has to be true, but if P is not true, then Q can be whatever it wants, no promises. My next example, here I've paraphrased the paraphrased. If you're a fan of The Office, there's a sort of a popular statement by Michael Scott where he paraphrases Wayne Gretzky. I had to paraphrase it a little bit further. So I've written it this way. I wanted to write it in a way that's very ambiguous. In this case, it says, if you take a shot, then you can score a goal. Not exactly what Wayne Gretzky said, famous hockey player. He said something along the lines of you never score on a shot you don't take, something like that. See, now I've even butchered it even further. Okay, but I've taken it, I've transformed it logically into this statement: if you take a shot, then you can score a goal. The interesting thing about this is this is a normal English usage, but let's put it through our own logic computer. So if you take a shot, does this mean you're going to score a goal? It says you can score a goal. Okay, so in this case, if you take the shot, if P is true, then we don't know about scoring a goal. You might score a goal or you might not. Okay, what about the other case? If you don't take the shot, can you score a goal? Now, if you're a hockey fan, you're like, well, it might bounce off your butt or something like that. Okay, I'm not talking about that. Okay. The idea here is if you don't take the shot, you're not going to score. You're guaranteed to not score. So Wayne Gretzky was saying this to try and encourage people. He said, why do you score so much? Or why do you shoot so much? You know, why are you always shooting all the time? Well, you're not. If you don't take the shot, you're not going to score, right? And so that's actually going to turn this implication around backwards. We actually see this the other way around. If you scored a goal, then it meant you took the shot. See how I said that? I've turned this sentence around. I've reversed it. If you scored a goal, then you took a shot. Okay, it put things temporally backwards. Here I'm saying if you take a shot, then in the future you might score a goal. If I put this backwards, I say if you scored a goal, then in the past you must have taken a shot, right? Because that's how time works. That's how hockey works, right? But this sentence is logically equivalent if we put it backwards. Okay, and that's what this logical statement up here, that's why the arrow points backwards here. It's the same thing as above, we've just set it backwards. Okay, it's if Q then P. And so all that means is when they're both true, they're still true. When they're both false, they're still false. But we've swapped the true and the false here. Okay. The last ambiguity, so this is one ambiguity, this one can really mess people up, although this one's not as common. And again, I think the ambiguity between these two, in English, if you're listening, the word can, I think, is the signal in English here that's telling you the difference between these two, okay? And again, most of our intuitive logic brains inside our head are already going to capture this no problem when we're listening to people express it in logic. It's now when we want to codify it, write it down in variables with symbols, we want to make sure we get it correct. Okay, the last one was the biconditional, and here I've got sort of another promise from your mom. If you're sitting at the table and you say, I want ice cream, you know, but you haven't finished your vegetables, your mom's going to say something like, if you finish your vegetables, then you can have ice cream. Well, that is sort of a both direction kind of if and only. It's saying, if you finish your vegetables, then you will get some ice cream. But if you don't finish your vegetables, you're not getting any ice cream. That's what we're trying to say here. And that's why if your mom is explaining it to you and you're 4 and you don't understand it, that's why she's going to explain it to you that way. She's going to say, if you finish your vegetables, then you can have the ice cream. But if you don't finish your vegetables, then you won't have your ice cream. And that's because the 4-year-old is training their internal logic computer themselves. The one that, again, hopefully you've already trained yourself. And so they're saying, your mother is reinforcing this truth table. It's saying you're only getting ice cream if you do finish your vegetables, and if you don't, you're not. Okay, so expressing exactly when this statement would be true. Okay, so this is an ambiguity, again, with implication, and that, again, is an ambiguity in natural language, but an ambiguity that we dispel, if you will, when we start writing things with propositions in propositional logic. All right, I think I've tackled propositional logic enough in this video. Thanks a lot for watching. In the next video, I'm going to explore truth tables in a little bit more detail to show how two logical sentences are equivalent, meaning express the same thing. And I've said that a few times in this video. I've just mentioned it a few times in talking about ambiguity here. How do we know when two sentences are equivalent, express the same meaning, have the same logical value? That's what we'll take a look at in the next video. So thanks a lot for watching, and we'll see you in the next video.